Far beyond the warmth of Earth, beyond the orbit of Mars, beyond the shattered rocks of the asteroid belt, there is a world wrapped in ice. It circles the giant planet Jupiter once every few days, hidden beneath crushing radiation and endless darkness. From a distance, it does not look alive. It looks silent, frozen, ancient, the kind of place the universe abandoned billions of years ago. And yet, something beneath its surface refuses to die. For decades, scientists believed moons were simple objects, dead rocks, frozen leftovers from the violent birth of the solar system. They were expected to be geologically inactive, chemically exhausted, and eternally cold. Worlds without stories. But Europa changed that assumption. Because beneath Europa's cracked shell of ice lies something almost impossible. An ocean, not a lake, not pockets of water trapped underground. An ocean larger than all the oceans on Earth combined, hidden beneath miles of frozen crust, completely sealed away from sunlight for perhaps 4.5 billion years. And recently, humanity looked at that ocean more closely than ever before. When the James Webb Space Telescope turned its mirrors toward Europa for the first time, scientists expected to refine existing models, maybe confirm a few chemical details, maybe improve measurements of the moon's surface. Instead, Webb found signs that the hidden ocean below may be far more active and far more Earth-like than anyone expected. The discovery was subtle at first. Tiny fingerprints in infrared light, traces of carbon dioxide concentrated in specific regions of the moon, strange salts scattered across broken landscapes, chemical patterns that did not behave like random contamination from space. The carbon appeared to be coming from inside Europa itself. And that changes everything, because carbon is not just another chemical. On Earth, carbon is the backbone of life. Every cell, every organism, every forest, every ocean creature, every human being is built on carbon chemistry. Webb did not discover life on Europa, but it discovered something unsettling. Europa appears to possess nearly every ingredient life would need: liquid water, energy, carbon, chemistry, time, and perhaps most disturbing of all, stability. Because Europa's ocean has likely existed for longer than complex life has existed on Earth. Somewhere beneath that frozen shell, chemical reactions have been running uninterrupted for billions of years in complete darkness. No sunlight has ever reached those waters. No eyes have ever seen them. No creature from Earth has ever touched them. The ocean has existed alone, hidden, waiting, and yet, the deeper scientists look, the less Europa resembles a dead moon and the more it resembles a living system. Its surface is fractured by enormous cracks stretching hundreds of miles across the ice. Great slabs appear to have shifted, broken apart, and frozen back together again like drifting sea ice over dark water. Entire regions look disturbed from below, as though something warm once pushed upward beneath the crust. These regions are called chaos terrains. The name is fitting because they look less like geology and more like evidence of a world struggling to breathe beneath its frozen skin. One of those regions, known as Terra Regio, became the focus of Webb's observations. And what Webb saw there startled scientists across the world. The carbon dioxide was not evenly spread across Europa's surface. It was concentrated, localized, connected directly to the broken terrain. That detail matters enormously, because if the carbon had come from asteroids or comets crashing into Europa over billions of years, it should have been spread randomly across the moon. But it was not random. It appeared connected to places where material from the deep interior may have reached the surface recently. In other words, Europa may be leaking. Slowly, quietly, its buried ocean may be communicating with the surface through fractures in the ice. And if chemistry from the ocean can rise upward, then someday spacecraft may be able to sample that chemistry directly. For the first time in human history, the search for alien life no longer feels entirely theoretical. It feels reachable. But Europa does not make things easy. The moon orbits deep inside Jupiter's radiation belts, one of the harshest environments in the solar system. Radiation constantly bombards the surface, tearing molecules apart, rearranging chemistry, and sterilizing exposed ice. Any ordinary organism from Earth would die there quickly. And yet, the strange thing is that radiation may actually help life deeper below. Because radiation striking the surface creates oxidants like oxygen and hydrogen peroxide. Over enormous spans of time, some of those chemicals may sink downward through the ice, eventually reaching the hidden ocean beneath. If that happens, Europa's ocean would possess not just water and carbon, but chemical energy sources similar to those used by life on Earth. The implications are staggering. Deep beneath the ice, there may exist an ocean where chemistry has been evolving in isolation since before multicellular life appeared on Earth. An ocean with its own cycles, its own energy, possibly even its own biology. And the terrifying part is this: if life truly emerged independently beneath Europa's ice, then life may not be rare in the universe at all. Because Europa is not unique. Astronomers now believe hidden oceans may exist throughout the solar system, beneath the icy crusts of distant moons, beneath frozen worlds orbiting giant planets around other stars. Entire ecosystems may be buried across the galaxy, invisible beneath layers of ice and darkness. For most of human history, we looked toward the stars and imagined alien life on distant planets under bright skies. But the universe may prefer oceans hidden underground, worlds without sunlight, worlds without civilizations, worlds where life survives silently beneath frozen shells for billions of years unnoticed. And somewhere beneath Europa's surface, beneath miles of cracked ice and black water, something may already be alive, not watching us, not knowing we exist, simply surviving in darkness while humanity slowly learns how to listen. But before we can understand what Webb discovered, we first need to understand how a frozen moon so far from the sun could possibly hide a living ocean at all. Because Europa should be frozen solid. And yet, somehow, it is not. At Jupiter's distance from the sun, sunlight is weak. The giant planet receives only a fraction of the warmth Earth does. Out there, temperatures plunge hundreds of degrees below freezing. Any ordinary body drifting through that region of space should have frozen solid billions of years ago. And most of them did. The moons surrounding Jupiter are, for the most part, ancient frozen relics. Worlds scarred by impacts and locked in deep geological sleep. No oceans, no atmosphere worth mentioning, no internal warmth. Europa should have joined them long ago. By every simple expectation, it should be a silent sphere of ice orbiting endlessly through darkness. But it is not, because hidden beneath Europa's frozen crust is a source of energy powerful enough to keep an entire ocean liquid for billions of years. And strangely, that energy does not come from Europa itself. It comes from gravity. To understand Europa, you first have to understand something deeply counterintuitive about the universe. Gravity does not only pull. Sometimes, gravity squeezes. Imagine holding a rubber ball in your hands. You press inward. The shape changes slightly. Then you let go. Then squeeze again. Over and over. The ball flexes. And every time it flexes, tiny amounts of energy turn into heat. Now scale that process up to the size of a moon. Europa orbits Jupiter in a slightly stretched path, not a perfect circle. During part of its orbit, the moon moves closer to Jupiter. During another part, it moves farther away. That difference may sound small, but Jupiter's gravity is immense. It is the largest planet in the solar system, more massive than every other planet combined. Its gravitational pull is so powerful that as Europa moves through its orbit, the moon is constantly being distorted. Stretched, relaxed, stretched again. The entire world flexes continuously. This ice shell bends. Its rocky interior strains. Deep inside the moon, friction builds as materials grind and deform under stress. That friction creates heat. Scientists call the process tidal heating. Without it, Europa would almost certainly be dead. But with it, the moon becomes something extraordinary. A water world. Deep beneath the ice, tidal heating melts the lower layers of Europa's frozen shell, creating a global ocean perhaps 60 miles deep. Underneath that ocean lies a rocky seafloor, warmed continuously by the same gravitational squeezing. And this is where the story becomes far stranger. Because on Earth, wherever water, rock, and heat come together, chemistry becomes active, very active. At the bottom of Earth's oceans are places known as hydrothermal vents. These vents form where seawater seeps into cracks in the crust, encounters hot rock below, and erupts back upward carrying dissolved minerals and chemicals. The water near these vents becomes rich in energy, and around that energy, life flourishes. Not life powered by sunlight, life powered purely by chemistry. When scientists first discovered hydrothermal vent ecosystems in the 1970s, the discovery shocked biology itself. Entire ecosystems existed in total darkness. Strange tube worms, bacteria, shrimp, and microbial colonies survived without any dependence on the sun. Before that moment, most scientists assumed sunlight was essential for life. The vents destroyed that assumption, and suddenly Europa no longer seemed impossible, because Europa appears to possess the same three critical ingredients: liquid water, warm rock, energy. The deeper scientists examined the moon, the more Europa began resembling a giant hidden laboratory for chemistry, and perhaps for biology as well. But there is another reason tidal heating matters. The heat inside Europa is not distributed evenly. Some regions receive more energy than others. Certain areas of the ice shell become thinner, warmer, and weaker. The surface above those regions cracks and shifts under stress, forming the strange, disrupted landscapes Webb later examined. Chaos terrains. The name sounds dramatic, but the appearance truly deserves it. Imagine enormous slabs of frozen ground shattered apart, tilted at strange angles, then frozen back into place as though the crust briefly softened beneath them. Some regions resemble drifting icebergs locked suddenly in time. These formations suggest something disturbing. Europa's shell is not static. The moon is active. The ice moves. The ocean below interacts with the crust above. And that interaction may allow material from the hidden sea to slowly rise toward the surface. That possibility is why the recent Webb observations caused such excitement. Because if chemicals from the ocean are reaching the top layers of Europa, then humanity may not need to drill through miles of ice to study what lies below. Europa may already be bringing pieces of its interior upward for us, quietly, over millions of years. But tidal heating creates another unsettling implication. Europa exists in an incredibly delicate balance. A little closer to Jupiter, and the heating might become catastrophic. The moon's interior could melt violently, producing a volcanic nightmare like Jupiter's neighboring moon Io, the most volcanically active body in the solar system. A little farther away, and the heating would weaken. The ocean would freeze solid forever. Europa sits almost perfectly between those extremes. Warm enough for water, cold enough for stability. For billions of years, the moon has remained trapped in this narrow zone where chemistry can continue uninterrupted beneath the ice. Some scientists describe this as cosmic luck. Others avoid that phrase entirely, because the more we discover about Europa, the harder it becomes to dismiss the possibility that environments like this may be common throughout the galaxy. Already, astronomers suspect there are countless hidden ocean worlds orbiting distant stars. Many may never possess civilizations or intelligent creatures. Some may host only microbes buried beneath ice. But if chemistry naturally becomes biology whenever the conditions are right, then the universe may be full of silent oceans where life emerged long before humanity existed. Europa is terrifying partly because it makes that possibility feel real, not abstract, not philosophical, real. And yet, despite everything scientists now suspect about Europa, we still have never seen its ocean directly. No submarine has entered those waters. No camera has touched the seafloor. Everything we know comes from indirect evidence. Magnetic signals, surface chemistry, infrared observations, geological patterns. We are reconstructing an entire hidden world from clues leaking through cracks in the ice. And recently, the clues became much harder to ignore, because the James Webb Space Telescope did not simply confirm frozen water on Europa. It found carbon chemistry concentrated exactly where the ice appears most disturbed, as though the ocean itself were pushing messages upward through the shell. And if that interpretation is correct, then somewhere beneath the surface of Europa, geological processes may still be active right now. Warm water may still be circulating. Minerals may still be reacting. Hydrothermal vents may still be operating on the seafloor in total darkness. The experiments beneath Europa's ice may still be running, uninterrupted, unknown. And perhaps, after billions of years, those experiments may have produced something far more complicated than chemistry alone. Because on Earth, chemistry once crossed a line. At some point in the ancient oceans of our own planet, molecules stopped merely reacting and began replicating. Life emerged, and that raises the question scientists cannot stop asking now. If it happened once beneath Earth's oceans, why could it not happen again beneath Europa's ice? For most of human history, Europa was only a dot of light, a tiny moving object beside Jupiter, barely distinguishable through early telescopes. Even after spacecraft finally reached the outer solar system, the moon remained mysterious, frozen, distant, difficult to study. Then the surface began revealing cracks. Not metaphorical cracks, real ones. Long dark fractures stretched across the ice for hundreds of miles. Strange broken regions appeared scattered across the moon like scars. Entire sections of the surface looked disturbed from below, as though something warm had once pushed upward through the frozen shell. Scientists slowly realized Europa was not geologically dead. But geology alone was not enough to transform the moon into one of the most important worlds in the solar system. The real shift came when chemistry entered the story, because chemistry is where habitability begins. And recently, the James Webb Space Telescope detected chemistry on Europa that should not have been there in the pattern scientists expected. At first glance, the discovery sounded simple. Carbon dioxide, that was the headline. Webb identified strong signatures of carbon dioxide frozen into specific regions of Europa's surface. To most people, carbon dioxide does not sound particularly exciting. Earth's atmosphere is full of it. Mars has plenty of it as well. But on Europa, location changes everything. Because the carbon dioxide was not spread evenly across the moon. It was concentrated in places where the surface ice appears youngest and most disturbed, especially in a region called Terra Regio. Terra Regio is one of Europa's chaos terrains, landscapes where the crust looks shattered, tilted, and refrozen. Massive blocks of ice appear to have broken apart and drifted before locking back into place. And directly within that region, Webb detected concentrated carbon chemistry. That detail terrified scientists in the best possible way, because it suggested the carbon was not arriving randomly from space. It was coming from below. This distinction is critical. Europa is constantly bombarded by micrometeorites, dust, and radiation. External contamination happens everywhere in the solar system. If the carbon dioxide came mainly from comet impacts or interplanetary dust, scientists would expect it to be distributed broadly across the moon's surface. But it was not. The chemistry seemed connected specifically to regions where the ice shell may interact with the hidden ocean underneath. And suddenly, the implications became enormous. Because carbon is one of the essential building blocks of biology. Not proof of life, not even close, but a necessary ingredient. And Webb's observations strongly suggested that ingredient is being transported upward from Europa's buried ocean. Then the discoveries became stranger. Alongside carbon dioxide, Webb also confirmed the presence of sodium chloride, ordinary salt, the same basic chemical family found in Earth's oceans. Now, salt itself is not biological. Oceans can form salts through entirely geological processes. But salt matters because it tells scientists something about water-rock interactions deep below the surface. Salt implies chemistry, complex chemistry, water interacting with minerals over long periods of time, the kind of chemistry capable of sustaining energy cycles. And then came another clue: hydrogen peroxide. Europa's surface is bombarded constantly by intense radiation from Jupiter. That radiation tears apart water molecules frozen in the ice, creating oxidants like oxygen and hydrogen peroxide. On the surface, those chemicals are destructive. But if even small amounts eventually migrate downward into the ocean, they could provide enormous amounts of chemical energy for possible organisms below. In other words, Europa may possess both sides of a biological energy system. Chemical reductants rising upward from hydrothermal activity near the seafloor. Chemical oxidants sinking downward from the irradiated surface. That combination creates disequilibrium. And disequilibrium is one of the defining characteristics of life-supporting systems. Earth's biosphere exists because energy flows between chemically different environments. Life feeds on imbalance. Europa appears to possess imbalance on a planetary scale. But perhaps the strangest discovery hidden inside Webb's data involved not the chemicals themselves, but the form of the ice surrounding them. Scientists expected Europa's surface to be dominated by amorphous ice. Amorphous ice forms under intense radiation. Molecules become disordered, chaotic, unable to settle into neat crystal structures. In environments like Europa's surface, radiation should gradually damage and randomize exposed ice over time. And yet Webb also detected large amounts of crystalline ice, organized ice, fresh ice that should not survive long in Jupiter's radiation environment. This created a disturbing implication. Europa's surface must be renewing itself continuously, because crystalline ice exposed to Jupiter's radiation should eventually become amorphous. The fact that both forms exist together suggests fresh material is regularly reaching the surface from below, or that regions of the crust are being warmed and recrystallized. Either explanation points toward ongoing activity, not ancient activity, current activity. Europa is changing now. The moon is not frozen in geological time. And once scientists began combining all these clues together, a coherent picture started to emerge. An ocean below, heat from tidal flexing, water-rock interactions near a warm seafloor, chemical transport upward through fractured ice, radiation-generated oxidants at the surface, fresh ice replacing older damaged material. Every individual clue could still be explained geologically, but together the system began looking eerily Earth-like. Not Earth-like on the surface. Europa's surface is a radiation-blasted frozen wasteland. But deep underneath, the moon increasingly resembles environments on Earth where life thrives without sunlight. And that realization forced scientists to revisit one of the biggest assumptions in biology. What if sunlight is not the main requirement for life in the universe? On Earth, sunlight dominates the surface biosphere. Plants harvest solar energy. Animals depend on plants directly or indirectly. Entire ecosystems trace back to the sun. But Europa may represent a completely different model. A world where biology, if it exists, survives entirely underground, powered not by starlight, but by planetary chemistry. That possibility changes how humanity searches for life everywhere else. Because suddenly, planets inside habitable zones are no longer the only important targets. Icy moons matter. Buried oceans matter. Darkness may not prevent biology at all. In fact, the universe may hide most of its life beneath surfaces rather than above them. And Europa may simply be the closest example. But there is another layer to the mystery web uncovered. One subtle detail hidden inside the carbon itself. Carbon atoms come in slightly different forms called isotopes. Most carbon in the universe is carbon-12. A smaller amount is carbon-13, which contains an extra neutron. Different physical and chemical processes prefer different isotopes slightly. That preference acts like a fingerprint. By studying isotope ratios, scientists can often determine where carbon originated. Comets produce one signature, planetary interiors produce another, and living organisms on Earth produce yet another. When Webb analyzed Europa's carbon dioxide, the isotope ratios suggested something remarkable. The carbon appeared consistent with internal planetary processing, not contamination from space, not random external delivery. The carbon likely originated inside Europa itself, deep below the ice, possibly from interactions between water and rock near the hidden ocean floor. And while the data did not reveal biology, it pushed the scientific conversation further than it had ever gone before. Europa was no longer merely a hypothetical ocean world. It had become chemically active, dynamic, potentially habitable in ways scientists could now directly observe. But chemistry alone does not create life. Energy matters too. And beneath Europa's ocean, at the very bottom of the hidden sea, there may exist environments far stranger than anything Webb could directly observe. Places where darkness, heat, minerals, and pressure collide. Places that on Earth may have given birth to life itself. Because the deeper scientists looked into Europa's chemistry, the more they began thinking about hydrothermal vents. 60 miles below Europa's frozen surface, beneath layers of cracked ice and beneath an ocean larger than all of Earth's combined seas, there may be a landscape no human being has ever truly imagined correctly. A seafloor, dark, rocky, pressurized beyond comprehension, and possibly alive. Everything about that hidden environment remains indirect. No probe has seen it. No sonar has mapped it. No submarine has entered Europa's waters. And yet scientists already believe the ocean floor may be the single most important location in the outer solar system. Because on Earth, places like it changed biology forever. When researchers first discovered hydrothermal vents deep beneath Earth's oceans in 1977, the finding shocked science. Before that moment, most ecosystems were understood through one simple chain. Sunlight feeds plants. Plants feed animals. Everything traces back to the sun. But at the bottom of Earth's oceans, thousands of feet below sunlight, entire ecosystems existed independently of it. Towering mineral chimneys erupted with superheated water rich in dissolved chemicals. Around them thrived strange organisms, giant tube worms, shrimp, bacteria, microbial mats. Life existed there in total darkness, not powered by light, powered by chemistry alone. And suddenly, Europa stopped seeming impossible, because Europa appears capable of creating remarkably similar conditions. Its rocky interior is continuously heated by tidal forces generated by Jupiter. That heating likely keeps parts of the seafloor geologically active. Water from the deep ocean may seep into fractures within the rock, become heated, react chemically with minerals, and rise back upward carrying energy-rich compounds. In other words, Europa may possess hydrothermal vents beneath its ocean right now. And if it does, then something deeply unsettling follows from that. Life on Earth itself may have begun in environments exactly like these. One of the leading theories for the origin of life proposes that Earth's first living systems emerged near ancient hydrothermal vents billions of years ago. Early Earth was violent and unstable. Volcanoes dominated the surface. Meteorites struck constantly. The atmosphere was toxic, but deep underwater, conditions were different. Stable, protected, chemically rich. Tiny molecular reactions occurred endlessly around warm mineral surfaces. Over immense stretches of time, some scientists believe those reactions crossed a threshold. Chemistry became biology. The first self-replicating systems appeared, and from those systems came every living thing on Earth. Now compare that ancient Earth to Europa, a rocky seafloor, liquid water, chemical gradients, heat, minerals, time. Europa has likely possessed these conditions for billions of years. That is the part many scientists struggle to ignore. Not because it proves life exists there. It does not. But because if life emerged naturally from chemistry on Earth under these conditions, then Europa may have been running the same experiment independently for almost the entire age of the solar system. And the experiment has remained hidden beneath ice the entire time. But what would that hidden world actually look like? Picture complete darkness. Not darkness like night on Earth where faint light still scatters through the atmosphere. True darkness, absolute absence of sunlight. Above, miles of water press downward with unimaginable force. The ice ceiling overhead seals the ocean completely from the outside universe. Near the seafloor, hydrothermal vents may rise like black towers, ejecting mineral-rich water hundreds of degrees hot into freezing surroundings. Clouds of dissolved chemicals billow upward through the ocean. Around those vents, chemistry becomes active, very active. If Europa resembles Earth even slightly, microbes could cluster around these energy sources in thin films or colonies, feeding on sulfur compounds, hydrogen, iron, or other chemicals released from the rock below. The organisms would likely be microscopic, slow-growing, efficient, Alien, but perhaps not entirely unfamiliar. Earth already contains extremophiles that survive in boiling acid, radioactive waste, deep underground rock, Antarctic ice, and crushing ocean trenches. Life, once it begins, appears astonishingly adaptable. That realization transformed astrobiology over the last few decades. Scientists no longer ask whether environments seem comfortable for humans. Humans are fragile, microbes are not, and Europa may provide everything microbial life truly needs. But the story becomes even stranger when scientists consider energy flow across the entire moon. Because Europa may possess not one source of chemical energy, but two: hydrothermal activity from below, radiation chemistry from above. As Jupiter's intense radiation bombards Europa's surface, it splits frozen water molecules apart. Oxygen and hydrogen peroxide form within the ice shell. If geological processes transport those oxidants downward into the ocean over time, then Europa's sea may contain chemical disequilibrium on a massive scale. And disequilibrium is crucial. Life feeds on imbalance. Organisms survive by exploiting differences between chemical states, temperatures, and energy levels. On Earth, oxygen-rich environments interact with chemically reduced materials from underground. Biology emerges between those extremes. Europa may possess similar gradients beneath the ice. That possibility dramatically increases the moon's theoretical habitability. And yet, despite how compelling the evidence has become, there remains a terrifying uncertainty hanging over all of it. No one knows whether the chemistry ever crossed the line into life. Europa may contain all the ingredients and still remain sterile. That possibility is deeply important, because if Europa is dead despite possessing liquid water, carbon, salts, energy, geological activity, and billions of years of stability, then something about Earth's history may have been extraordinarily rare. Perhaps life does not emerge easily after all. Perhaps habitability is not enough. And if that is true, then the universe could be far lonelier than humanity hopes. Scientists understand this tension very clearly. That is why every new Europa discovery creates both excitement and caution simultaneously. The evidence increasingly favors habitability. But habitability is not biology, at least not yet. Still, some features on Europa's surface continue pulling scientists toward the possibility that the ocean below remains active even now. One of the strangest of those features is called Connemara chaos. When spacecraft first photographed the region decades ago, researchers struggled to interpret what they were seeing. The terrain resembled shattered pack ice frozen suddenly in motion. Huge slabs appeared rotated, tilted, displaced from their original positions. Something had broken the crust apart from underneath, perhaps briefly melting sections of the shell, perhaps lifting warmer material upward before everything refroze. The region looked disturbingly young enough that similar events may still occur today. And if chaos terrains represent locations where ocean material reaches close to the surface, then they become extraordinarily valuable scientifically. Because drilling through Europa's entire ice shell may remain impossible for decades. Current estimates place the shell somewhere between several miles and possibly more than 20 miles thick. Even the lower estimates create engineering nightmares. Radiation, pressure, cryogenic temperatures, remote operation 500 million miles from Earth. For now, humanity cannot reach the ocean directly, so scientists have adopted a different strategy. Instead of drilling through the wall, study the places where the wall leaks. Chaos terrains may contain frozen traces of ocean chemistry transported upward naturally over geological time. Sampling surface ice there could effectively provide indirect access to the hidden sea below. And recently, the James Webb Space Telescope pointed directly at one of those regions. What it found did not confirm life, but it confirmed something else almost equally unsettling. Europa's chemistry is fresh, active, recent. The moon is still exchanging material between its hidden interior and its frozen surface. The system is alive geologically, and if the ocean beneath Europa has remained chemically active for billions of years, then somewhere under all that ice, the greatest biological experiment in the solar system may still be running right now. For decades, Europa existed mostly as a scientific possibility, a moon with intriguing cracks, a hidden ocean suspected beneath the ice, hints of chemistry, hints of heat, hints of habitability. But hints are dangerous in science. Hints inspire theories, documentaries, headlines, and speculation. Yet, without direct evidence, even the most exciting worlds remain uncertain. Then the James Webb Space Telescope arrived, and suddenly Europa stopped being merely hypothetical, because Webb was built for exactly this kind of investigation. Unlike older telescopes, Webb sees the universe primarily in infrared light. Infrared reveals chemistry. Molecules absorb and emit specific wavelengths in recognizable patterns, almost like fingerprints scattered through light itself. By splitting incoming light into spectra, scientists can identify the substances present on distant worlds without physically touching them. And when Webb turned toward Europa, researchers hoped for small refinements. Maybe clearer maps, maybe better surface detail, maybe confirmation of a few earlier observations. What they received instead was a much deeper glimpse into the moon's internal activity. The observations themselves were surprisingly brief, only minutes long. That is what makes the results so astonishing. In just a tiny amount of telescope time, Webb identified concentrated carbon dioxide signatures associated specifically with Terra Regio, one of Europa's major chaos terrains. Not randomly distributed, not globally spread, localized, fresh, connected directly to geologically disturbed regions. That detail changed everything, because it implied the chemistry originated internally. The logic was difficult to escape. If carbon dioxide came mainly from external contamination like comet dust or meteorite impacts, it should appear relatively evenly across Europa's surface. Impacts happen everywhere, but Terra Regio stood out, a place where the ice appears fractured, broken, and geologically young also happened to contain unusually strong carbon signatures. Scientists immediately recognized the implication. Ocean material may be reaching the surface there, and Webb was not finished. Alongside carbon dioxide, the telescope strengthened evidence for sodium chloride, ordinary salt, associated with the same regions. This mattered because sodium chloride behaves differently than many other surface compounds on Europa. Radiation tends to alter materials over time. The fact that salts appeared linked to younger chaos terrain suggested active replenishment. Fresh chemistry, fresh transport, fresh geological exchange. Europa's surface was behaving less like a frozen shell and more like a slowly breathing membrane between the hidden ocean and space. But perhaps the most important discovery involved something scientists had long debated unsuccessfully: the state of Europa's ice itself. Earlier missions hinted that Europa's surface might contain both crystalline and amorphous ice. Webb confirmed this far more clearly. To understand why that matters, you have to understand how radiation affects frozen water. Crystalline ice forms when water molecules organize neatly into repeating structures. It is stable under calm conditions. Amorphous ice forms under harsh radiation or extremely rapid freezing. The molecules become disordered, chaotic, unable to align properly. Near Jupiter, radiation levels are extreme. Over time, exposed crystalline ice should gradually become amorphous. And yet Europa contains both, which means one unavoidable thing: the surface must be renewing itself continuously. Fresh crystalline ice must be reaching the surface faster than radiation can fully damage it. Somewhere beneath the shell, processes remain active enough to constantly reshape parts of the moon. This finding was subtle compared to the dramatic headlines about carbon dioxide. But scientifically, it may be even more important, because it transformed Europa from a world that was once active into a world active right now. Present tense, not ancient geology, current geology. And current geology means current energy transfer, current ocean exchange, current chemistry. The moon is alive in a planetary sense. That realization triggered a measurable shift within the scientific community. Before Webb, Europa was considered one strong candidate for extraterrestrial habitability. After Webb, many researchers quietly began treating it as the strongest candidate in the solar system. Not because anyone had discovered life. They had not. But because every new layer of evidence kept pointing toward conditions that on Earth would be extraordinarily favorable for biology. And then scientists noticed another deeply intriguing clue hidden within Webb's measurements. Carbon isotopes. Carbon exists primarily as carbon-12 and carbon-13. Different processes slightly favor one isotope over the other. Biology on Earth preferentially uses lighter carbon-12 during metabolism, creating recognizable isotope patterns. Webb's measurements could not confirm biological fractionation. The data simply was not precise enough for that. But the isotope ratios strongly suggested the carbon originated inside Europa itself rather than arriving from space. That distinction mattered enormously, because internal carbon means the hidden ocean is chemically active. The ocean is not isolated. It is interacting with rock, transporting material, possibly sustaining cycles similar to those that once existed on early Earth. And suddenly, the scientific discussion expanded beyond Europa itself. Because if Europa possesses these conditions, how common might similar worlds be across the galaxy? That question changed the scale of the mystery entirely. For most of history, scientists searched for life mainly on Earth-like planets orbiting within habitable zones around stars. The assumption was simple. Life needs sunlight, liquid water near the surface, moderate temperatures. But Europa challenged that framework completely. Its ocean exists beneath ice. Its energy comes largely from tidal heating rather than sunlight. This chemistry may operate entirely underground. And if life can emerge under those conditions, then the universe may contain vastly more habitable environments than previously imagined. Icy moons become important. Subsurface oceans become important. Darkness no longer disqualifies biology. Suddenly, worlds once dismissed as frozen dead objects transform into potential ecosystems. And our own solar system contains several of them. Enceladus ejects enormous water plumes into space. Titan possesses complex organic chemistry and hydrocarbon lakes. Ganymede likely contains a deep-buried ocean larger than Earth's oceans combined. Europa is simply the nearest and perhaps most accessible example. Webb's discoveries intensified interest in all of them simultaneously. But Europa remained different, because Europa appears to balance on a knife edge between frozen stability and geological activity. Too much tidal heating and it would resemble volcanic Io, where lava dominates the surface. Too little heating and the ocean would freeze solid forever. Europa exists in a narrow middle ground where liquid water persists beneath an icy shell for billions of years. A remarkably delicate arrangement. And some scientists began privately admitting something uncomfortable. The conditions seemed almost too good. Liquid water, carbon, salts, oxidants, geological transport, long-term stability, potential hydrothermal activity, fresh chemistry. Every major requirement for life appeared present simultaneously. Not proof, but increasingly difficult to dismiss. Still, Webb had limitations. The telescope could identify chemistry and broad surface patterns, but it could not directly probe deep beneath the ice, could not sample the ocean, could not detect cells or organisms. It was listening to Europa from very far away, reading subtle traces in reflected light. To move further, humanity needed something else. A spacecraft capable of approaching Europa directly, flying low over the surface, scanning the ice, tasting the thin atmosphere, searching for chemical signatures at close range. And by the time Webb released its discoveries, that spacecraft was already on its way. In October of 2024, a machine the size of a basketball court rose slowly from Earth and disappeared into the sky. Its destination was not a planet, not a star, not even open interstellar space. Its destination was a frozen moon hidden deep inside the radiation fields of Jupiter. A moon humanity now increasingly suspects may harbor the conditions for life. The spacecraft was called Europa Clipper, and it represents one of the most ambitious scientific missions ever attempted. For decades, Europa existed mostly as a mystery viewed from a distance. Telescopes could observe the surface. Earlier probes could photograph cracks and chaos terrains during brief flybys. Scientists could build models and argue theories, but no spacecraft had ever been designed specifically to investigate Europa in detail. Clipper changes that completely. The spacecraft itself is enormous by planetary mission standards. Its giant solar arrays stretch nearly 100 feet from tip to tip, larger than many commercial airplanes. That size is necessary because sunlight near Jupiter is incredibly weak. At Earth's distance from the Sun, solar panels work efficiently. At Jupiter, sunlight drops to only a tiny fraction of what reaches our planet. Clipper must collect every available photon just to power its instruments. And those instruments are extraordinary. Each one was designed around a specific question scientists desperately want answered. How thick is the ice shell? What chemicals exist on the surface? How active is the ocean beneath? Does material move upward from the sea below? Could the moon actually support life? Some instruments will photograph the surface in resolutions far beyond anything humanity has ever seen before. Others will measure heat leaking through the shell. Others will map the magnetic field induced by Europa's hidden salty ocean. But perhaps the most anticipated instrument aboard Clipper is the mass spectrometer. Because if Europa's surface or atmosphere contains traces of complex organic chemistry, this instrument may find them. Europa technically possesses an atmosphere, although calling it an atmosphere almost feels misleading. It is unimaginably thin, more like a faint cloud of particles constantly created as radiation strips molecules away from the ice surface. Yet that thin veil may contain clues from the ocean below. As Clipper repeatedly flies past Europa, around 50 close flybys over several years, the spacecraft will pass directly through this environment, sampling particles molecule by molecule. Scientists are not expecting dramatic cinematic discoveries. No giant creatures, no visible ecosystems. The real search is subtler: chemical disequilibrium, organic complexity, patterns that geology alone struggles to explain. Because life leaves fingerprints even when life itself remains invisible. And Clipper is designed specifically to search for those fingerprints. But the mission's importance extends far beyond biology alone. One of Clipper's central goals is simply understanding how Europa works as a world. For example, scientists still do not know exactly how thick the ice shell truly is. Some estimates suggest only a few miles in certain regions. Others suggest 20 miles or more. The answer changes everything about future exploration. A thinner shell might someday allow robotic melt probes or drilling systems to reach the ocean directly. A thicker shell transforms the challenge into something vastly more difficult. Clipper's ice-penetrating radar may finally resolve this debate. The radar system will send signals deep into the ice, mapping internal layers, fractures, and possibly pockets of trapped liquid water hidden within the shell itself. And that possibility opens another fascinating chapter in the Europa story. Because Europa's ocean may not be the only liquid water environment beneath the surface. Some scientists now suspect the ice shell contains shallow lakes trapped between layers of frozen crust. Evidence comes partly from strange structures called double ridges, long parallel ice walls stretching across the moon for hundreds of miles. Researchers studying similar formations in Greenland found that such ridges can form when shallow water pockets freeze and deform the ice above them. If Europa operates similarly, then liquid reservoirs may exist much closer to the surface than the deep ocean itself. That would matter enormously, not only scientifically but practically. A shallow lake buried within the ice would be far easier to access than an ocean dozens of miles below. It could contain chemistry transported upward from deeper regions while remaining protected from intense surface radiation. In some ways, these hidden lakes could become intermediate laboratories between the ocean and the surface world above. Clipper's radar may detect them directly, and if it does, the implications would ripple through planetary science instantly. Because suddenly Europa becomes even more dynamic than previously imagined. Not a frozen shell above a buried sea. A layered, circulating system filled with movement. Movement matters. Habitability depends on transport. Energy must flow. Chemicals must circulate. On Earth, oceans, atmosphere, and geology constantly interact. Europa may possess slower versions of similar cycles beneath its ice. And if those cycles exist, then biology, if present, would have access to far more chemical opportunities than scientists once believed. But Clipper faces enormous challenges before it can answer any of these questions. The biggest is radiation. Jupiter possesses the most intense radiation environment in the solar system outside the Sun itself. Charged particles trapped in the giant planet's magnetic field bombard Europa continuously. A human standing unprotected near Europa would receive a fatal radiation dose very quickly. Electronics suffer too. Radiation damages circuits, degrades instruments, corrupts memory systems. Engineers spent years designing Clipper to survive this environment. Sensitive electronics are shielded inside vaults lined with radiation-resistant materials. Mission planners carefully designed flyby trajectories to minimize exposure whenever possible. Even so, Europa remains one of the harshest environments any scientific spacecraft has ever attempted to study closely. And yet the risk was considered worth taking, because the scientific stakes have become enormous, especially after Webb. Before the James Webb observations, Clipper was already exciting. After Webb confirmed fresh carbon chemistry associated with active chaos terrains, the mission acquired a new level of urgency. Clipper now arrives with targets, specific regions, specific chemical anomalies, specific mysteries demanding explanation. Terra Regio became particularly important. The chaos terrain where Webb detected concentrated carbon dioxide and salts may represent one of the best places to study material originating from Europa's interior. If fresh ocean chemistry is leaking upward anywhere, scientists suspect regions like this are where it happens, and Clipper will repeatedly pass nearby. There is even a small possibility, one scientist discussed carefully and cautiously, that Clipper could fly through an active plume if Europa possesses eruptive activity similar to Enceladus. Earlier observations by the Hubble Space Telescope hinted at possible water plumes erupting intermittently from Europa's surface. The evidence remains uncertain. Webb has not yet confirmed them, but if plumes exist and Clipper encounters one, the spacecraft could directly sample material from beneath the ice without needing to drill at all. Ocean chemistry thrown naturally into space. It would be one of the greatest scientific opportunities in modern planetary exploration. Still, scientists remain careful not to overpromise. Clipper is not a life detection mission in the purest sense. It is a habitability mission. Its primary objective is determining whether Europa truly possesses conditions capable of supporting life. And that distinction matters, because discovering habitable conditions is not the same as discovering organisms. Yet even habitability alone would transform humanity's understanding of the universe. If Europa proves strongly habitable, then icy ocean worlds across the galaxy may suddenly become major candidates in the search for extraterrestrial life. Thousands, millions, possibly billions of hidden oceans may exist beneath frozen shells orbiting distant planets around distant stars. And somewhere among them, chemistry may have crossed into biology countless times. Clipper cannot answer all of those questions, but it may answer the first one: whether the ocean beneath Europa is merely chemically interesting, or whether it is the kind of place where life could genuinely survive. And while Clipper speeds silently outward through space, another spacecraft from another continent is following close behind, because humanity is no longer searching Europa alone. While Europa Clipper crossed the darkness between Earth and Jupiter, another spacecraft was already traveling toward the same distant system, not from NASA, from Europe. In April of 2023, the Jupiter Icy Moons Explorer, better known simply as JUICE, launched aboard an Ariane rocket and began its own long journey outward. Its mission is broader than Clipper's. Where Clipper focuses almost entirely on Europa, JUICE was designed to study multiple icy moons around Jupiter, especially Ganymede, the largest moon in the solar system. And yet Europa remains one of JUICE's most important targets, because something unusual has happened in planetary science over the past 2 decades. The search for life has slowly migrated away from planets, toward moons. For most of human history, moons were treated as secondary objects. Beautiful perhaps, interesting perhaps, but scientifically less important than planets themselves. Europa changed that perception forever. Then Enceladus strengthened it. Then Titan complicated it even further. And now scientists increasingly suspect that the most habitable environments in the solar system may not exist on planetary surfaces at all. They may exist hidden beneath ice, protected from radiation, warmed internally, sealed away in darkness for billions of years. That realization reshaped exploration priorities across the world. And now, for the first time in history, two major interplanetary missions are traveling simultaneously toward the same family of ocean worlds. Different spacecraft, different instruments, different agencies, but one shared question: could life exist there? The existence of both missions at the same time matters enormously, because science becomes much stronger when independent teams using different equipment arrive at similar conclusions. If Clipper detects unusual chemistry and JUICE confirms it, confidence increases dramatically. If JUICE sees evidence of internal activity in one region and Clipper later observes the same thing from another angle, the picture sharpens. Together, the missions create something rare in planetary science: redundancy. And redundancy is powerful because Europa is frustratingly difficult to study. The moon hides almost everything important beneath miles of ice. Scientists cannot directly observe the ocean. They cannot directly photograph the seafloor. They cannot directly measure hydrothermal vents. Everything must be inferred indirectly through surface features, chemistry, magnetic fields, heat patterns, and tiny traces leaking outward from below. Europa is essentially a locked world. Humanity is trying to understand an entire hidden environment by studying the cracks in its ceiling. That challenge changes the psychology of the scientists involved. Because unlike many areas of astronomy, Europa research feels intensely close to something tangible. Researchers are not studying abstract equations or unimaginably distant galaxies. They are studying a real ocean, a real environment, possibly a real ecosystem, an entire hidden world sitting within our own solar system. And that proximity creates emotion. Scientists rarely speak dramatically in formal papers. Scientific language remains careful, restrained, and precise. But privately, many researchers admit Europa affects them differently, because the implications feel immediate, not theoretical, immediate. If life exists there, then life emerged twice independently within a single solar system. That would mean biology is probably not rare. It would mean the galaxy may be filled with living environments. The philosophical consequences become difficult to overstate. For centuries, humanity treated life as something unique to Earth. Even after discovering planets around other stars, uncertainty remained enormous because we possessed only one known example of biology. One data point, Earth. Europa could change that forever. And yet, paradoxically, the moon also inspires another feeling: loneliness. Because if life exists beneath the ice, it has existed entirely alone. No sunlight, no sky, no awareness of the stars above. Imagine organisms evolving for billions of years inside a sealed ocean without ever seeing the universe beyond their own dark water. No civilizations, no telescopes, no concept of planets or galaxies or suns. Just chemistry and survival beneath endless ice. That idea unsettles people in ways difficult to fully explain. An entire biosphere potentially existing beside us cosmically speaking, while remaining completely unaware that anything else exists. And now, suddenly, another species has begun listening. That asymmetry changes the emotional texture of the Europa story. Humanity may become the first intelligence in the universe ever to know Europa's ocean exists, including possibly the organisms within it. And that possibility raises questions extending far beyond science. Suppose future missions eventually confirm life. What then? How should humanity interact with another biosphere? Should we explore aggressively, protect it, leave it untouched? Even microbial ecosystems possess enormous scientific value. Introducing Earth microbes accidentally could permanently contaminate Europa's native chemistry before we fully understand it. This concern already shapes spacecraft engineering today. Both Clipper and JUICE undergo strict planetary protection procedures designed to minimize biological contamination. Components are sterilized carefully. Trajectories are planned to avoid accidental impacts after missions end. Scientists understand the stakes. If Europa contains life, it may represent one of the few completely independent biological experiments in the known universe. Contaminating that experiment carelessly would be an irreversible mistake. And yet, the desire to explore remains overwhelming, because humans are curious by nature, especially about life, especially about origins. Europa matters not only because it might contain organisms now, but because it may preserve clues about how life begins at all. Many origin of life researchers believe Earth's earliest biology emerged near hydrothermal vents deep beneath ancient oceans. Before plants, before oxygen, before complex ecosystems, chemistry near hot mineral-rich water may have slowly crossed the threshold into self-replication. Europa possesses remarkably similar conditions: rock, water, heat, chemical gradients, time. Perhaps that is enough. Or perhaps Earth possessed some additional ingredient Europa lacks. That uncertainty sits at the heart of modern astrobiology. And it explains why Europa inspires such intense attention. Because either outcome rewrites humanity's understanding of life. If Europa contains biology, then life likely emerges naturally whenever conditions become suitable. If Europa remains sterile despite favorable conditions, then the emergence of life may require something extraordinarily rare. Either answer transforms science. Either answer changes how humans view themselves. And both Clipper and Juice exist because humanity finally reached the technological point where such questions can be investigated seriously rather than philosophically. That transition is historically extraordinary. For thousands of years, people could only speculate about life beyond Earth through religion, philosophy, or imagination. Now spacecraft carrying advanced spectrometers and radar systems are physically traveling toward another potentially habitable ocean. The question has entered the realm of measurement, and still the mystery deepens, because the more scientists learn about Europa, the stranger the moon becomes. The surface appears geologically young in many regions, meaning it continuously renews itself. Chaos terrains suggest active exchange between deep ice and surface layers. Double ridges hint at internal lakes trapped within the shell. Magnetic data strongly supports a salty global ocean. Webb revealed fresh carbon chemistry associated with active geological regions. Each discovery alone would be important. Together, they create an increasingly coherent picture of a world that is not frozen and dead, but dynamic, circulating, active, possibly habitable right now. And perhaps the most unsettling realization of all is this: Europa has likely remained this way for billions of years, longer than multicellular life has existed on Earth, longer than dinosaurs, longer than mammals, possibly long enough for entirely separate evolutionary histories to unfold beneath the ice. Not civilizations, probably not complex animals. The energy budget may be too limited for that, but microbes, microbial ecosystems, slow chemical evolution across geological time? Those possibilities no longer sound speculative in the way they once did. They sound plausible, and that shift from science fiction to plausible science may be the real reason Europa feels so psychologically powerful. Humanity is not merely imagining alien oceans anymore. We are preparing to investigate one directly. And while Clipper and Juice travel silently outward through interplanetary darkness, telescopes back on Earth continue watching the moon closely, because the next clue may arrive before either spacecraft even reaches Jupiter. And some scientists suspect the most important discoveries have not happened yet. For all the excitement surrounding Europa, one fact remains unavoidable. We still do not truly know what is happening beneath the ice. That uncertainty is important, because science advances not only through discoveries, but through the recognition of what remains unexplained. And Europa is overflowing with unanswered questions. Some of them are technical, some geological, some chemical, some philosophical, but together they form a strange picture, a world that appears increasingly alive in a planetary sense while refusing to fully reveal itself. Take the ice shell itself. Scientists often speak about Europa's crust as though it were a single structure, but the reality is probably much more complicated. How thick is it? The honest answer is that nobody knows for certain. Some models suggest regions only a few miles deep. Others predict shells approaching 30 miles thick in places. That difference changes everything. A thinner shell allows easier transport between ocean and surface. Cracks could penetrate deeper. Heat could rise more efficiently. Future robotic exploration becomes more realistic. A thicker shell creates a far more isolated ocean, almost completely sealed away from the outside universe. And the evidence points in both directions simultaneously. Chaos terrains imply regions where the shell weakened dramatically. Double ridges suggest shallow internal water pockets. Thermal measurements hint at uneven heating. Meanwhile, gravity models sometimes favor a more substantial crust capable of supporting large-scale surface structures. Europa refuses to simplify itself. Every answer branches into new contradictions. And then there are the plumes. For years, astronomers debated whether Europa ejects water vapor into space like Enceladus. The Hubble Space Telescope detected tentative signs of towering water plumes rising from the Moon's southern regions. If confirmed, those plumes would change exploration entirely, because they would provide direct access to ocean material without drilling through miles of ice. A spacecraft could simply fly through the plume and sample the particles directly. It would be one of the greatest opportunities in planetary science. But confirmation never came cleanly. Some observations appeared promising. Others showed nothing. Even Webb, despite its extraordinary sensitivity, has not definitively detected active plumes yet. So what is happening? Perhaps the eruptions are intermittent. Perhaps they only occur during specific points in Europa's orbit when tidal stresses peak. Perhaps they are smaller than expected. Or perhaps the earlier detections were misleading entirely. Scientists still do not know. And that uncertainty creates a strange tension around Europa research. The Moon repeatedly behaves like an active ocean world. Yet every time researchers approach certainty, the evidence becomes ambiguous again. It is as though Europa reveals clues deliberately while hiding the conclusion. Then there is the chemistry itself. Webb detected carbon dioxide, salts, and oxidants associated with chaos terrains like Terra Regio. But why exactly that combination? Why concentrated there? What specific geological process is producing these distributions? Researchers can build models, but no single explanation fits every observation perfectly. Some scientists believe warm upwellings from the ocean carry dissolved materials upward through the shell. Others favor shallow melt pockets trapped within the ice. Still others suspect multiple transport mechanisms operating simultaneously across different regions. Europa may not possess one unified geological system at all. It may possess many overlapping systems interacting in ways we barely understand. And beneath everything lies the biggest unknown of all, the seafloor. Scientists talk constantly about Europa's hidden ocean, but oceans alone are not enough for life. Interaction matters. On Earth, the relationship between water and rock drives enormous amounts of chemistry. Hydrothermal vents release minerals, heat, and chemical gradients capable of powering entire ecosystems without sunlight. If Europa's ocean directly contacts a rocky seafloor, similar processes could occur there too. But we have never seen that seafloor. Not once. Every assumption about it comes indirectly from measurements of mass, density, and magnetic behavior. For all we know, the bottom of Europa's ocean could resemble Earth's volcanic ridges. Or it could be radically different. Different minerals, different chemistry, different energy flows, possibly conditions far less favorable for biology than researchers currently hope. This uncertainty becomes especially important when discussing hydrothermal vents. The idea of Europa vent ecosystems is compelling because Earth's vents support life extremely well. But similarity is not proof. Earth biology evolved under Earth conditions. Europa may differ in crucial ways. Its pressure may be far greater, its chemical gradients weaker, its mineral composition unfamiliar. Even small changes could dramatically alter whether biology becomes possible. And yet, despite all these unknowns, the evidence keeps leaning toward activity, toward movement, toward exchange. Europa does not look chemically dormant. That is what makes the uncertainty so psychologically powerful. Because the moon sits directly between two possibilities: a second genesis of life, or a sterile world that somehow almost became alive but never crossed the threshold. Both outcomes are profound. Imagine if future missions confirm that Europa possesses all the conditions associated with life: water, energy, organics, stable chemistry, and still remains completely dead. That result would force scientists to rethink the entire origin of life problem, because it would imply habitability alone is insufficient. Something else would be missing, some hidden requirement. Perhaps life needs surface environments exposed to cycles of drying and wetting. Perhaps sunlight plays a deeper role than expected. Perhaps Earth simply got unimaginably lucky. If Europa is sterile despite billions of years of opportunity, then life itself may be extraordinarily rare. And that possibility frightens many researchers more than alien life ever could, because it implies Earth might be exceptional on a cosmic scale, possibly even unique nearby, a lone biological island in an otherwise silent universe. But the opposite possibility feels equally overwhelming. If Europa contains life, then biology emerged independently twice within one solar system. And if it happened twice here, probably happened everywhere, across billions of stars, across endless oceans hidden beneath distant ice. The universe would suddenly become crowded with invisible ecosystems, most likely microbial, most likely simple, but alive. The implications would ripple through philosophy, religion, and culture for centuries. And yet, frustratingly, Europa may refuse to give us a clear answer anytime soon. That possibility is increasingly discussed among scientists themselves, because real discoveries are often messy. Clipper may detect intriguing organic molecules without proving biology. JUICE may observe suspicious chemistry that still permits geological explanations. Future landers may find patterns suggestive of metabolism without definitive confirmation. Humanity could end up trapped in an uncomfortable middle ground. Strong evidence, no proof, hints everywhere, certainty nowhere. That scenario may sound disappointing, but scientifically it is extremely plausible. Nature rarely organizes itself conveniently around human expectations, especially in environments this remote and difficult to study. And Europa's isolation magnifies every challenge. Unlike Mars, where rovers can drive across landscapes directly examining rocks, Europa hides its secrets beneath a frozen barrier. Everything important exists below. Everything accessible exists above. Scientists must reconstruct the hidden world from leaks, fractures, chemistry, and indirect measurements, like detectives investigating a sealed room through cracks beneath the door. And still, despite all the uncertainty, the momentum continues building. More Webb observations are scheduled. More laboratory simulations are underway. Researchers are recreating Europa chemistry inside controlled environments on Earth, testing how salts, radiation, and water interact over long timescales. Every year, the models improve. Every year, the mystery sharpens. But perhaps the strangest realization is this: Europa has probably been waiting the entire time. For 4.5 billion years, the moon orbited Jupiter in silence, while its hidden ocean evolved unnoticed. Long before humans existed, long before Earth possessed intelligent life, possibly long before complex life emerged here at all. Whatever chemistry operates beneath Europa's ice has been operating continuously through almost the entire history of the solar system. And only now, in the tiniest recent fraction of cosmic time, another species has begun listening carefully enough to notice. That realization changes the emotional tone of the story. Europa no longer feels like a distant astronomical object. It feels like an unopened world, a sealed experiment, a dark ocean carrying answers humanity has wanted since the beginning of civilization. Answers about life, about rarity, about whether biology is an accident or a natural feature of the universe itself. And somewhere beneath the ice, hidden from every telescope ever built, the experiment is still running right now. When people imagine alien life, they usually imagine something dramatic. Towering creatures beneath black oceans, intelligent beings hidden under the ice, gigantic organisms swimming through Europa's dark waters beneath the frozen shell. But the reality, if life exists there at all, is almost certainly much quieter, much smaller, and in some ways far stranger, because the most likely inhabitants of Europa are not monsters. They are microbes, tiny single-celled organisms living slowly in darkness beneath miles of ice. At first glance, that may sound disappointing, but to scientists, microbial life would already represent one of the greatest discoveries in human history, because it would mean biology emerged independently beyond Earth. And that single fact would change humanity forever. Still, to understand what Europa life might actually look like, we first need to understand something important. Life does not require sunlight. That idea surprises many people because Earth's surface ecosystems depend heavily on the sun. Plants capture sunlight through photosynthesis. Animals eat plants. Predators eat animals. The entire visible world ultimately traces back to solar energy. But deep beneath Earth's oceans, another type of ecosystem exists entirely separate from sunlight. Around hydrothermal vents on the seafloor, hot mineral-rich water rises from cracks in Earth's crust. The water carries chemicals like hydrogen sulfide, methane, iron, and other compounds capable of storing chemical energy. Their entire ecosystems survive purely through chemistry. Bacteria harvest energy directly from chemical reactions. Tube worms, shrimp, crabs, and strange translucent creatures depend on those bacteria. No sunlight ever reaches these places, and yet life thrives. This discovery transformed biology when scientists first encountered it in the 1970s, because suddenly, the conditions required for life seemed far broader than previously imagined. And Europa appears to possess many of the same ingredients: a rocky seafloor, liquid water, internal heat generated by tidal forces from Jupiter, possible hydrothermal activity, chemical gradients, oxidants delivered downward from the radiation process surface. All the fundamental pieces seem present, which means if biology emerged there, it likely resembles Earth's extremophiles far more than anything from science fiction. Extremophiles are organisms that survive in conditions once considered impossible for life. Some live in boiling acidic springs. Some survive inside Antarctic ice. Some feed on rock miles underground. Some tolerate radiation levels that would instantly kill humans. Earth keeps revealing that life, once established, is astonishingly adaptable. That adaptability is one reason Europa seems increasingly plausible as a biological environment. Not comfortable, not Earth-like in the ordinary sense, but survivable. Still, Europa's ocean would impose severe limitations. Energy availability is probably low compared to Earth's surface ecosystems. Sunlight-driven biology can generate enormous amounts of energy quickly. Chemical ecosystems are slower and thinner. That matters because complexity requires energy. Large animals require lots of food. Fast movement requires high metabolic output. Complex nervous systems consume enormous resources. Europa may simply not possess enough available energy to support large multicellular ecosystems. That is why most scientists expect microbial life at best. Slow-growing colonies clustered near hydrothermal vents. Thin biofilms coating rocks. Perhaps free-floating microorganisms drifting through the ocean. Possibly ecosystems so sparse that vast stretches of water remain nearly empty. And yet, even this modest vision becomes emotionally overwhelming when considered carefully. Imagine it, an entirely separate tree of life evolving beneath Europa's ice for billions of years. Not descended from Earth organisms. Not related genetically, a second genesis. Every cell operating through biochemistry born independently elsewhere in the solar system. Even if the organisms resemble bacteria superficially, their internal biology could differ dramatically. Perhaps they use unfamiliar amino acids. Perhaps their cell membranes function differently. Perhaps their metabolism exploits chemical pathways Earth life never discovered. Or perhaps, intriguingly, They resemble Earth biology closely because chemistry itself strongly constrains how life can emerge. That question matters enormously, because if alien life resembles us chemically, it suggests biology across the universe may follow predictable rules. If it differs radically, then life may be capable of forms humanity has barely imagined. Either answer would revolutionize science. There is another possibility too: panspermia. Some researchers wonder whether life might travel naturally between worlds through impacts. Large asteroid collisions can eject rocks into space. Some microbes on Earth survive extreme conditions surprisingly well. In theory, primitive organisms might occasionally survive journeys between planets or moons. Could Earth and Europa share ancient microbial ancestry somehow? Most scientists remain skeptical because the environments differ enormously and transport opportunities appear limited. But the possibility cannot be fully dismissed. If Europa life were discovered and shared deep biochemical similarities with Earth organisms, this question would become unavoidable. Did life begin twice independently, or once, spreading between worlds? And that possibility introduces another unsettling thought. Perhaps the solar system has been biologically connected longer than humans realize. Still, before any of these questions can be answered, scientists must first detect life at all. And that challenge is extraordinarily difficult, because chemistry alone can mimic biology surprisingly well. Organic molecules are not proof of organisms. Amino acids form naturally in space. Meteorites contain complex carbon compounds without life being involved. Even isotope signatures, while powerful, can sometimes emerge through non-biological processes under unusual conditions. This is why astrobiologists speak carefully about biosignatures. A biosignature is not simply a molecule. It is a pattern difficult to explain without biology. On Earth, one powerful example is the simultaneous presence of oxygen and methane in the atmosphere. Those gases react with each other chemically. Without constant replenishment, methane disappears quickly. Their coexistence implies active processes maintaining imbalance. Life creates that imbalance. Scientists searching Europa are looking for similar forms of disequilibrium, unexpected combinations, persistent complexity, chemical ratios difficult to sustain geologically. The ladder of evidence matters here. At the bottom are hints, conditions favorable for life. Europa already satisfies many of those. In the middle are organic compounds and suspicious chemical patterns. Clipper may detect some of these. At the top lies definitive proof: cells, metabolism, reproduction, something unmistakably alive. Humanity has not reached that level yet, and perhaps not reaching it immediately may become the most psychologically difficult outcome of all, because the evidence may slowly accumulate without crossing the threshold into certainty. Imagine future headlines: Europa mission detects intriguing organic chemistry. Scientists report possible biological isotope ratios. New data suggests active chemical cycling beneath ice. Each discovery pushes suspicion higher. Each discovery increases tension, but none fully resolves the mystery. That scenario could persist for decades. A world increasingly suggestive of biology without definitive confirmation. And perhaps that uncertainty itself is part of why Europa captivates people so deeply. The moon exists at the edge of revelation, close enough to imagine clearly, far enough to remain inaccessible. Every discovery sharpens the outline without fully illuminating the center. And meanwhile, beneath the ice, the ocean continues existing in total darkness. If organisms live there, they do not know they are being searched for. That asymmetry remains haunting. Humanity may become aware of Europa life long before Europa life becomes aware of humanity, if awareness is even possible for such organisms at all. Tiny microbes drifting through warm mineral plumes beneath miles of frozen crust would possess no concept of planets or stars or galaxies. And yet their existence alone would answer one of civilization's oldest questions. Are we alone? Perhaps not. Perhaps life emerges wherever chemistry and time cooperate long enough. Perhaps the universe is filled with silent oceans beneath silent ice shells orbiting distant worlds around distant suns. most containing only microbes, some perhaps more, and perhaps somewhere far beyond Europa, another intelligence is asking the same question while staring at another hidden ocean beneath another frozen sky. But before humanity begins imagining distant alien civilizations, we must first confront something much closer. Because the discovery of even microbial life on Europa would fundamentally alter how humans understand themselves. And the consequences of that realization would spread far beyond science alone. Somewhere beneath the frozen crust of Europa, an ocean is moving in darkness. No human has seen it. No probe has entered it. No light from the sun has ever touched its depths. And yet, for billions of years, that hidden sea has existed quietly beneath the ice while the universe changed above it. Empires rose on Earth. Species appeared and vanished. Dinosaurs ruled and disappeared. Human civilization emerged only yesterday in cosmic terms. All the while, Europa continued orbiting Jupiter every few days, its frozen shell flexing endlessly under gravitational stress, its hidden chemistry running in silence. That realization is difficult to fully absorb. There may be an entire environment, possibly even an entire biosphere, existing beside us within our own solar system that remained completely unknown for almost all of human history. And now, suddenly, humanity has begun listening closely enough to hear faint signals escaping from beneath the ice. That is what changed after the observations from the James Webb Space Telescope. Not because Webb discovered life. It did not. Not because Webb solved Europa's mysteries. It did not. What Webb changed was subtler and perhaps more important. It shifted Europa from possibility into plausibility. The strange concentrations of carbon dioxide associated with chaos terrains. The evidence for fresh chemistry rising from below. The presence of salts and oxidants in regions where the shell appears geologically active. The hints that the surface is constantly renewing itself faster than radiation can destroy it. Individually, these findings are fascinating. Together, they paint the outline of a world that no longer feels frozen and dead. They paint the outline of a system, a functioning environment, a place where chemistry, water, energy, and time have interacted continuously for nearly the entire history of the solar system. And perhaps that is why scientists sometimes describe Europa as horrifying. Not horrifying in the sense of fear, horrifying in the older meaning of the word. Something immense, something overwhelming, something that forces you to confront how strange reality actually is. Because Europa transforms the search for life from abstraction into geography. For centuries, humans imagined alien life as something impossibly distant, hidden around stars we could barely observe. But Europa is here, close enough that spacecraft can reach it within a human lifetime, close enough that telescopes already read the chemistry of its surface, close enough that right now, at this very moment, 2 spacecraft are traveling outward to investigate it directly. That changes the emotional scale of the question entirely. We are no longer wondering vaguely whether life exists somewhere in the universe. We are preparing to investigate a specific ocean on a specific moon around a specific planet in our own sky. And the answer, whatever it is, may arrive within the lifetimes of people alive today. That alone makes this one of the most extraordinary moments in scientific history. But there is another layer to the Europa story that feels almost philosophical. Because either outcome changes humanity profoundly. If future missions discover life beneath Europa's ice, then biology is likely common throughout the cosmos. Life would no longer appear miraculous in the rare sense. Instead, it would seem natural, a process chemistry falls into whenever conditions become favorable. The galaxy would suddenly feel crowded with hidden ecosystems, not necessarily civilizations, probably not vast alien empires, but oceans, microbes, countless worlds where chemistry crossed into biology long before humans ever existed. The night sky would become biologically alive in a way previous generations could barely imagine. And if Europa proves sterile, that answer may be even more unsettling, because Europa appears to possess many of the ingredients associated with habitability: liquid water, carbon compounds, internal heat, energy gradients, geological activity, billions of years of stability. If all of that still fails to produce life, then perhaps life itself is extraordinarily rare. Perhaps Earth was not inevitable. Perhaps the emergence of biology requires something incredibly unlikely, something fragile, something precious. That possibility changes humanity's position in the universe too. Suddenly, Earth becomes not merely home, but anomaly, a rare island of awareness surrounded by cosmic silence. Either conclusion reshapes civilization, either conclusion permanently alters how humans understand themselves. And yet, perhaps the strangest possibility is that Europa refuses to give us a clean answer at all. Science rarely unfolds dramatically in a single moment. More often, certainty arrives slowly through years of frustrating ambiguity. Clipper may detect suspicious organic chemistry. JUICE may confirm active geological transport. Future landers may identify compounds suggestive of metabolism. And still, none of it may fully cross the threshold into proof. Humanity could spend decades staring at increasingly compelling evidence without complete certainty. That uncertainty might become its own kind of haunting. Knowing something extraordinary is probably happening beneath the ice, without being able to say definitively what it is. But regardless of the outcome, one fact already remains permanent. Europa changed the way humans think about worlds. Before missions like Galileo, icy moons were considered frozen leftovers of planetary formation. Today, they are among the most promising habitats in the solar system, and Europa sits at the center of that transformation. A moon once ignored now carries some of the biggest scientific questions humanity has ever asked. Questions about origins, about biology, about rarity, about whether life is a cosmic accident or a cosmic rule. And somewhere beneath miles of fractured ice, the hidden ocean continues moving in darkness, completely unaware that another species has finally begun searching for it. That detail may be the most unsettling of all. If life exists there, it has existed entirely alone for billions of years. No communication, no knowledge of stars, no awareness of galaxies, just chemistry unfolding endlessly beneath black water. And now, from far above, another intelligence has noticed. For the first time in the history of the universe, as far as we know, one world may be looking consciously toward another hidden living ocean. The story is not finished. Europa Clipper is still traveling. Jupiter Icy Moons Explorer is still approaching. Webb continues watching from deep space. Scientists continue modeling the chemistry, the ice physics, the ocean circulation, the possibility of hydrothermal systems beneath the seafloor. Thousands of people across dozens of countries are dedicating their lives to understanding what lies beneath Europa's shell. And somewhere ahead, perhaps in a quiet scientific paper, perhaps during a NASA press conference, perhaps buried inside lines of cautious technical language, humanity may eventually encounter one of the most important sentences ever spoken. We found life, or we did not. Either answer will echo for centuries. Either answer will change what it means to be human. But for now, the ocean beneath the ice remains silent. The chemistry continues. The shell flexes and cracks. The hidden sea breathes slowly beneath the frozen surface. And 500 million miles away from Earth, in total darkness, the experiment is still running.